Get ourselves started with the sessions for Day 2 of Haskell Exchange 2020. First up is Richard Eisenberg, who is here with some great instruction on how to simplify constraint solving in GHC or the Glasgow Haskell compiler. Please welcome Richard.
Hi, everyone. It's great to be here and to be presenting this morning about, or this afternoon or this evening, depending on where you are, about GHC. I'm broadcasting from the suburbs of Philadelphia in the U.S. So just as a little way of background, oh, wait, you can't see my slides, can you? But if I click here and then click here, then I think you can. Good. Okay, there we are. By way of introduction a little bit, so I'm a researcher at Twig, and my day job, or part of my day job as a researcher at Twig, is actually working right on GHC. And so I spend quite a bit of time thinking about how can GHC do a better job at accepting our good programs and rejecting our bad programs. This presentation is the result of some recent work I've been doing in actually simplifying things. It's fantastic. There's 2 patches in flight right now that I've been working on with collaborators, chiefly Simon Peyton-Jones, to remove what should hopefully add up to be thousands of lines of code from the type checker, while also making things better and faster. So this is it's very nice to be able to remove code. It's the only thing better than adding lots of really well-working code is to remove lots of code and still keep things working well. Okay, so that's sort of the background behind this. This particular talk is going to be an exploration of how GHC uses constraints to perform type inference. Right, we want to sort of understand that just as useful background. Right, it'll help us to understand our interactions with GHC a little bit better, knowing all of this. And then I'll also on the way explain these 2 simplifications. So this is hopefully going to be a good example-driven talk. This is actually my last slide because we're going to spend the rest of the time in Emacs. So I've popped over. Hopefully that is big enough here. Okay, so we're going to walk through, and the other thing that I try to do in this talk is really not assume very much Haskell at all. Technical experience is good because we're going to be doing some technical concepts here, but Haskell itself actually not as much. So let's get started. So here's a very basic example. Let's walk through it together. We obviously have some imports up here at the top. And then I have a class. It's just like show, but I thought it would be nice to have everything self-contained here. So we have stringable and its method to string that allows us to convert any type into a string. And we say that integers are stringable. And here the implementation, yes, it's using the built-in show, but that's not the important part. We also have a stringable instance here for lists. So we're going to say that any list is stringable as long as the element itself is stringable. And again, we're just not going to care so much about the implementation. It does the thing that you think it does. And then here, I'm going to assume that some type A is stringable. That's what this little bit says here, is that we're going to assume that in the body of 3 string. And then in the body of 3 string, I call this toString function on a list of 3 elements. But what's interesting here is I've assumed that A is stringable, but I haven't said anything about whether lists are stringable, at least not very locally right here. So this program, let's test it. This compiles. I should say this GHCI that I'm using is just stock GHCI. This is 8.10.1. There's nothing fancy going on down here. And I'll show you whether things are meant to compile or not. Most of my examples are meant to compile. And so the question is, how does this work? How does GHC actually make this happen? And so the way that it works is using the idea of given constraints and wanted constraints. So in this particular case, we have a given that A is stringable. So this given, it's labeled with this G over here. G is for given. W will be for wanted. And that corresponds to this. We're going to assume that A is stringable. But here, where I call toString on this list, well, toString is a method in the stringable class. So that means that we need to know that the argument type is stringable. So we end up with a wanted stringable list of A. And then the goal in GHC, this constraint solving, is all about solving the wanteds from the givens. So at this point, we already learned something interesting. So I said that we use constraint solving to perform type inference. And actually, in this particular example, there is no, if you sort of look out broadly enough, it doesn't look like there's any type inference going on in this example, right? The one function I've defined, three-string, has a type signature. Well, in GHC and in other languages, type inference includes more than just figuring out what is the top level type of something. It's also about figuring out all of these other details that we leave out. So one detail that's left out is that we have multiple instances for stringable, and there might be other instances that could be imported, right? This is a very small example, but we could imagine something bigger. And it's to figure out which instance we're going to use. It's also to figure out, whenever we have a polymorphic function like toString, what type are we going to instantiate it at? So toString can work for any A. Well, what type do I mean here? Well, I really mean list of whatever this A is here. And so type inference includes those processes too. And so some people like to say, Agda or Idris, they don't do type inference because they require top-level signatures. I would respectfully disagree with that. I'd say they do type inference. It's just it's a more limited form of type inference than GHC. If I were pressed to sort of try to characterize it, I would say those languages don't do what's called let generalization. In other words, if we leave out a type, it can't infer a general type for their definitions. But they still, I would say, do type inference. Getting back to this example here, so we have this wanted and this given. Well, how are we going to solve this? How are we going to then prove the wanteds from the givens? Well, in this case, it's quite easy. We take this wanted and we use the top level instance. And that top level instance says that as long as stringable A is true, then stringable list of A will be true. And so here, if I want stringable list of A, then this says that I really just want stringable A. So I would get a new wanted stringable A, and then that's solved by assumption. So here, now I've used my wanted to prove my given, and then I can accept the program, and I know to use this instance down here in practice. Okay, so that's this example. Let's move on to example number 2. Here's example number 2. So here we have class equable and class ordable, right? This is very similar to eq and ord in the Haskell prelude, but again, I wanted it to be self-contained. And so here we see that ordable has a superclass equable. And so in Haskell, what this means is that we're guaranteed that if there is a type that is ordable, if I have an instance for ordable, then there will always, always, always be an instance for equable for that same type. That's what this superclass constraint means. It also means that when I have a given ordable, if every type that has an instance for ordable also has an instance for equable, then if I know ordable, I can assume equable. So this program compiles. Let's look at the givens and the wanteds. So here I get a given of ordable A, and then in the body of is reflexive, this uses the equals method here. So that's going to induce a wanted equable A. And we know it's A, by the way, because this type signature tells us what the type of our argument is. It says that it's A. So that means this X here has that type A, and we're applying equals to X. So we get wanted equable A here. Now, how do we solve this? If I look at my given doesn't say anything about equable. But actually, the way that GHC works is GHC does eager expansion of given superclasses. Or maybe even eager expansion of superclasses of givens. Probably slightly more accurate. And so, not only do I get a given ordable A, I get a given equable A. And now this is very easy. I can solve this wanted by assumption. And so we see here in examples 1 and 2, sometimes, in effect, GHC reasons backwards from the wanteds, and sometimes GHC reasons forwards from the givens. So we have this rather complex constraint solver inside of GHC that has grown over time to handle all of these different cases. And that's the area where these patches that I mentioned toward the beginning are really working on. Okay, one thing to note here, when I say eager expansion, I really mean that. So you can imagine having a Haskell program with lots and lots of superclass relationships among the classes, and then you can actually induce some exponential behavior if you have them depending on each other in bad ways, because it really just does eager expansion. Okay, but that example is somewhat simpler. So here we have example 2. Let's look at example 3. Okay, so now we've seen examples dealing with classes, but actually GHC doesn't just use its constraint solver to deal with class constraints. It uses its constraint solver to also deal with equalities. And that's really the power. In fact, under the hood, GHC uses its constraint solver for just about everything. Those of you who've been following along with quick look impredicativity and the fact that impredicativity has been so hard in GHC, the reason it's been hard is that it doesn't necessarily fit so well with this constraint solving model. We had to come up with something else to do that. I'm not going to get into details there. But most of the time, every time we dream up a new feature to work in GHC, type inference centers on how can we generate and then solve constraints. So for this example here we have invert. It's just like not from the prelude, but self-contained. Now let's look at what givens and wanteds we get. So this case is different in that f has no type signature. So if I'm defining something without a type signature, we're going to guess that f has type alpha. And so within GHC, we use this notion of unification variable. And a unification variable is just a stand-in for a type that we don't know what it is yet. So f has some type. We don't know what it is yet. So we're going to name it alpha. And this allows us, by giving it a name, this allows us to maybe have multiple occurrences of it that sort of flow through our program. And then later, we might figure out exactly what it is. And I'm going to use Greek letters to denote unification variables throughout this talk. So here we guess that f has type alpha, but then right away we see, well, as I define it, f is applied to something. So I don't know what the type of that is yet, but we're going to get a wanted that alpha must equal some beta going to some gamma, right? Alpha has to be a function type. And this is before I ever get to the right-hand side, just because I see that f is applied to something on the left. So right away, we get this wanted. Later, when we solve, we're going to say, well, solving a wanted that involves one of these unification variables tends to be quite easy because we can just choose what that unification variable can be. So we're going to choose alpha to be beta arrow gamma. And that solves the wanted. Because if I want alpha to equal beta arrow gamma, and I could just choose it. So actually internally, GHC uses the IO monad and does mutable update here because that's more efficient than building up a substitution, which would be the alternative. So we could do this very purely and instead over time build up a substitution that maps alpha to something like beta arrow gamma and then apply the substitution at the end. But we don't do that. Instead, we just use mutable cells. Still, we do have to apply the substitution. Which means go through all of the types within GHC and rewrite all occurrences of alpha with the thing that we solved it for, beta arrow gamma. That's called zonking. If anyone has looked inside of GHC and sees this mysterious thing called zonking, that's just rewriting something like alpha with beta arrow gamma. Just taking these unification variables and replacing them by their contents. There's a little bit more involved with zonking, but that's 90% of it. Okay, so we figured this out. We figured that alpha really needs to be beta arrow gamma just from this x. And then now we also know that if the type of f is beta arrow gamma, we also can learn that x has type beta, and the right-hand side has to have type gamma. And so these aren't really constraints that I'm writing here. That's why I'm not writing a wanted or a given, but these are relationships that GHC is tracking internally. Now we could get to finally look at the right-hand side, and we see that there's this invert function. And so the invert function tells us that we're going to get wanted beta is bool, and wanted gamma is bool, right? This comes from the argument of invert, and this comes from the result of invert. Right? We see that x is used as the argument to invert. X has type beta. Invert expects a bool, so we get that beta must equal bool, and similarly, the result of invert is a bool, and so we get that gamma is a bool. And then so we choose beta to be bool, gamma to be bool, and we're all done. And we can solve all of our constraints. Okay, so here's this example of a quality constraint working for us, but it's going to get a little bit more challenging. Let's look at the next example. Number 4. Okay, so here I've imported 2 functions from the prelude, ord and not. So ord has type char arrow int, not has type bool arrow bool. And I've defined 2 functions, f and g, no type signatures. And in both, I've called ord x and not x. If I compile this, I get errors. That should not be a surprise, because x can't be both a char and a bool. What's interesting here is that in function f here, it says that couldn't match expected type bool with actual type char. Okay, that's fairly reasonable. It's unable to match bool with char. In G, however, can I get this wrong button? There it is. There, I can get it all on the screen. So down here, for G, right, we see that this is G. It can't match expected type char with actual type bool. So what is this expected and actual? The idea is within GHC is that when we have an expected type, that's the type essentially expected by the context. So the error in F is in not, right? Not expects a bool as its argument. Char, rather, ord expects a char as its argument. So why do we say actual type char here? Well, that's saying that X has type char. But why does X have type char? So let's put these error messages away just for a moment and look at some wanteds and givens. So in F, what we see here is that we're going to quickly get that X. I'm not going to start out with F having type alpha like I did last time. We're going to skip some steps. So if I say here, we're going to just say X has some type alpha, and then we're quickly going to get a wanted alpha is char. We get that from the use of X as the argument to ord, and we get a wanted alpha is bool, and we get that from the use of X as an argument to not. The way that GHC will go through and solve these, it just solves them in the same order that they arise. As it turns out, that's not something we work hard to maintain. We could imagine maintaining that, but in practice, there's nothing that flips the list, right? So we end up processing left to right here. And so we'll choose alpha is char. And then by the time, then our second wanted, we're going to rewrite that to char equals bool, and that's the error that we report. And at that point, we've said that the type of X is char, and so that's why we have actual type char here. In G, it's the other way around. And that's why in the error for G, let's bring these errors up again. So in the error for G, we get actual type bool, and that's because here X is inferred to have type bool because the first thing that we see is that it's expected to have type bool. So the reason I think this is interesting is that the order of our code, right? If we sort of look abstractly, F and G are sort of the same function. There's really no difference between them. Order shouldn't matter. And it's an important property as we're designing GHC and as writing the constraint solver that order won't matter to whether programs are accepted or not, and if they are accepted, to what they mean. other than sort of obvious things that, if I have a list, the order in the list matters, right? But it shouldn't matter to type inference. Yet it does matter to error messages. Because the way that the constraint solver works will change what our error messages produce. We want it not to matter very much, right? So sometimes we do take steps that maybe there's a program that can error in multiple different ways, and we do want it not to be order dependent. Here, we have not done anything in particular to stop the order dependency between inferred or between expected and actual, and so we see two different errors here. But what this is also suggesting is that the particular details of how the constraint solver is written can affect the error messages that users see. It turns out that's a major driving force of some aspects of the complexity of the constraint solver is how can we do all of this solving while still, in the end, if we fail to solve, present something interesting to the user. Okay, so that's this example. I'm not going to walk through G. It would not be very illuminating at this point, but we'll close that comment off. Okay, let's move on. We're actually going to skip examples 5 and 6. I don't think that they're all that necessary. This talk, this was a sort of a late addition to the agenda here, and this was originally designed for a slightly longer slot. So we're going to skip this. I don't think that they're as important. Maybe we can come back to them in the Q&A afterward. But I'm going to jump to number 7 here, and we need a little bit more space. Okay, so now we're going to get into a new aspect of GHC, and that's called type families. So this is a program that is expected to compile here. A type family is declared with some syntax like this, and this is declaring capital F as a function on types. So maybe we would define that f int equals bool, or maybe we would define that f car equals list of maybe of double, right? This is going to be a function on types. The important thing for type inferences is that we don't really know how it's going to operate, and so we have to take that into account as we do type inference. So let's look at some of the constraints that arise as we're looking at f and g. So let's look at f first. And here, let me just, instead of just jumping over it, the inject function just takes an A and produces an FA. And this is convenient in building examples, right? The definition of inject is bogus, and there isn't really a good way of writing this in this program. So the programs become a little bit more contrived from this point. Well, they've already been pretty contrived, haven't they? But the goal is to come up with simple examples, not realistic examples, which tend not to be simple. So in F here, we're going to say X has some type alpha. We don't know what it's going to be. And then we see not inject X. Okay, so, well, inject, that works for any type A. So that's not going to induce any constraints, but not expects a bool. So we're going to get a wanted that the argument type to not, well, what's the argument type to not? Well, it's the result of inject. So in this case, if X has type alpha, the result of inject is going to have type F alpha, and then we're going to end up wanting F alpha to equal bool. So previously, when we had constraints involving metavariables like this, we would just say, oh, let's just choose alpha to be something. We can't do that for this particular wanted because I don't yet know how F operates. And in particular, F might not be injective, right? This wanted may not be enough information for me to determine what alpha is. So that means I can't just choose alpha at this point. So from this wanted, the way that GHC works today is it says, well, I don't know what's going on here, but I said earlier that these type functions, they should be any type out there. We don't really know what they're going to be. So since we don't know what they're going to be, what GHC does is it does a flatten operation. So it's going to flatten this constraint to become wanted f alpha equals fmv and wanted fmv equals bool. So I'm just going to draw a little line here to say what it was before, and this is what it becomes. So FMV stands for flatten metavariable. And the idea here is that every time we see one of these type families, we say, well, I don't know what that is, so I'm going to just invent a new variable. And because a type family application, right, the result of a type family can be anything at all, I'm going to represent that by a fresh variable. And so here we're going to say f alpha is some FMV. We don't know what it is, but we also need the FMV to be bool. It turns out there's no way of solving these wanteds, right? But yet the program is accepted. So how is that? Well, what GHC will do is if it has a case like this where f does not have a type signature, but we have some unsolved wanteds, it will try to quantify over those wanteds. So we could have done this also with class constraints. It's very simple over class constraints. But here the idea is that, well, we can't solve this, but we can maybe assume it in the inferred type for f. The process is a bit involved, but we'll say in the end, what happens is we're going to say, okay, this FMV, we don't want to present that to the user. That's a bit ugly. So we're going to recombine it and sort of get rid of that FMV after constraint solving in a process called unflattening. And we're going to infer f has type fa equals bool. That's enough information to satisfy this constraint. And then it takes some a and it's going to return some bool. Right? And if I compile my program and ask what is the type of f, that's exactly what we see. And the reason that GHC infers this is because it has an unsolved wanted, which it can then quantify over. G is similar. In G, we get x has type alpha, and we also get that we get a wanted here that f alpha equals alpha. So the reason we get that is because all elements in a list must be the same. So if x has type alpha, then that must match the type f alpha. So we get this wanted f alpha equals alpha. We flatten. We're going to get f alpha is some fresh FMV, and then we get a wanted FMV equals alpha. These constraints are actually a little bit nicer in that they don't mention the same thing on either side. An equality that mentions the same thing on either side is a bit funny to work with. So this is another reason why we have flattened in the past. As a spoiler for what's to come, we're going to get rid of this flattening step. Makes things much simpler. But anyway, we flatten for now, and then again we can't solve these wanted, so we're going to abstract over them, and then we infer that G has type fa equals a to, I guess, list of a. And let's see, did I get that right? Yes, I did. And again, I think this is quite clever that GHC can infer a type with an equality like this, where both sides of the equality mention a. It's also worth pointing out that because a equals fa, if I wrote fa over here instead of a, that would also be correct. But GHC is going to choose the simpler a here. Okay, so now we're starting to see how we can work with constraints and type families. Let's move on to number 8. Okay, so now in number 8, things are starting to get a little bit more complicated because now we have both type families and classes and overlapping instances. It turns out we don't need overlapping instances to make this example work, but it makes the example much simpler to use overlapping instances than various other constructs I could have built this with. So the idea here is that I have a class C. It has one method, meth, that just takes the argument A. And this is really just sort of a toy construct that allows me to easily produce a wanted constraint that mentions C. Of course, there's 2 instances. In this more general instance, this will work for list of A for any A, but I want specific behavior, say, if I have a list of bool. Maybe I want that to be different. In this case, this method is so trivial that there's no way of making a difference. But maybe in the general case, I do. I guess I could make some small difference. I could make it strict. That's probably going to complain about bang patterns or something. Let me not try to edit the code in that way. That's just going to make things more complicated. But we could imagine that one of these is strict and one of these is lazy if I wanted some small difference. But the point here is that the choice of the instance might matter at runtime. So we want to be careful when choosing instances. We have our same type family F from the last example. We have the same inject from the last example. And then now we have this F here that we're going to try to infer types for. So this, as written, it's going to have an error. This is actually an example that we're meant to get an error in. And the error is that we get an overlapping instance for C of F, a C of list of FA, and the reason for that is that we don't know which one of these to choose. So let's look at the wanteds and the givens to try to understand this. So actually, there's no givens in this case. We just have wanteds. So once again, we start with X having type alpha. That's not quite a constraint, so I won't write it that way. X has type alpha. So then we're injecting X. So we have inject X has type F alpha. List of inject X has type list of F alpha. But then meth is being called on that. And if meth is a method inside of our class C, then that's going to induce a wanted C of list of alpha. And we can't solve that. And so because we can't solve that, in this case, we also can't abstract over this because there's not quite enough information to do so. Again, I don't want to get into the details of exactly how we sort of infer those top level types. That's a different talk. But I'm just going to say we can't do the simple trick that we were doing in the last slide. And so the real problem here, though, is that while we do have a way of solving C of list of A, we also have a way of solving C of list of bool. And in the end, we can't choose which of these is more appropriate because we don't know what F of alpha is going to be. So even though it looks like we should be able to solve anything with C of list of A, we want to hold out the possibility that F of A might be bool. So the way that happens in practice is, once again, we're going to flatten to get a wanted F alpha equals FMV and a separate wanted C of list of FMV. Then we're going to try to solve this class constraint. And when we try to solve this class constraint, what GHC does is it looks for any instance that might apply. And it sees, well, this one applies, and this one applies, right? Because I don't know what FMV is. And so I could use this top instance right away. I can't use this because I need to know FMV is bool. But maybe later I will learn that FMV is bool. And if FMV really is bool, I'd want to use this instance. So instead of committing to something that might be wrong, GHC is very careful to never make a mistake. Right? Sometimes it prefers to take no action at all over making a mistake. This is also because GHC does not backtrack. Right? We might imagine that we can try to solve things using backward reasoning, for example, and say, when we get stuck, oh, just try a different path. GHC never, ever does that. And that's because that kind of backtracking can quickly lead to exponential behavior. And we don't want exponential behavior within GHC. So in this case, when we try to solve, we just fail. There's not enough information to do this. So again, the interesting thing here is that this FMV, by using flattening, it allows us to see that both of these instances might apply. Previously, when it's just F of A, well, bool and F of A look quite different. And so it means in our effort to remove flattening, we're going to have to take special care here. Okay, let's move on to example 9. Okay, so in example 9, let's see. This one compiles. So here in example 9, we have our type family FA again. And now, in this case, we're not trying to infer the top level type for F, we're given it. So let's look at our wanteds and our givens. So here we get a given FA is bool. And then in our body, we have X. According to the type signature, X has type FA. So I'll write that down here. Note that A here is A. It's not alpha. It's some abstract type A. We know that it has to work for any type, right? A is still distinct from alpha here. It's not a unification variable. But x is used here as the argument to not. So that means we're going to get a wanted fa equals bool. And the way that GHC uses these equalities internally isn't just, it looks very easy here. It's like, oh, why don't we just solve the wanted from the given? Well, we could do that, but the general way that GHC does this is by doing rewriting. So we're first going to flatten. And so this flatten becomes a given fa equals. So for givens, we use things called FSKs, which stands for flattened scolum. I'm going to keep my slides or this presentation accurate, even if it's a little confusing. We can just pretend FSK and FMV are the same. In 99% of cases, they're treated the same internally. So we're going to flatten this into that, and then a separate one, FSK, is bool. Then down here in our wanted, this also flattens. And then this is going to flatten into FSK equals bool as well. So what's happening here is that we already know that FA is related to FSK. By the time we get to the wanted, there's this table that GHC builds up internally to relate type family applications to either flattened metavariables or flattened scolums. And so we get this wanted. Then we end up rewriting So when we rewrite with our given, we're going to get a new wanted bool equals bool, and that's very easy to solve. The idea here is that this second given, well, that's quite straightforward. We just have a variable equals a type. So when we have a variable equals a type, we can use that for rewriting, and we're going to use that down here. So the key innovation in getting rid of flattening is just rewrite type family applications. So the simplification is, let's get rid of these FSKs, let's get rid of these FMVs, and just use this directly to do rewriting. Instead of building a substitution from type variables to types, we can build a substitution from type family applications to types. It's a little bit different. It's maybe not what we're usually used to doing with substitutions, but we can. And so that this works actually quite nicely for the previous two examples. If we go back to example 7 here, right, this works really nicely. We don't need these FMVs. They just sort of got in the way. So this direct treatment of type family applications works much better. In example 8 here, it's a little bit harder because now we need to be careful when we look up F alpha. We have to say, well, F alpha and bool, maybe F alpha is bool, maybe it's not bool. And so a little bit of extra machinery has to go into that to make that work. This was sort of a bug in my patch, that originally it didn't catch this relationship that F alpha might become bool. So that could be problematic. But here we just add a little bit of extra machinery, much less than this FMV and FSK stuff. These FMVs and FSKs also sometimes leaked into type checker plugins. So anyone who's attempted a type checker plugin should be quite happy with this simplification. Okay, so that's one big simplification that I'm looking at inside of GHC right now. We have one last example, number 10 here. So in number 10, we have a type family F again. And then we have this function. So again, we're not trying to infer the type, but there's some bad type stuff going on in here. If I try to compile this, we're going to get an error message. And we can see that as we build our wanteds and givens. So here we have B has type FA, C has type FA. And if we look, we're going to get a wanted from ord B that we must have FA equals car. And we also get a wanted from the fact that C is being added to these others, that FA equals int. So naively, we might get car equals int. If we use rewriting to say rewrite one wanted with the other, we would get car equals int. And we might report that to the user. in practice, that can be very, very confusing because the real challenge is that it's FA that's either char or int, but it's not a direct conflict between char and int in our code. So we don't want this error. The way that GHC avoids doing this is using a technique called derived constraints. The idea, quite quickly, I'm running out of time here, but the idea quite quickly is that we're going to get, instead of just these wanteds, we also get this other form of constraint called derived. And the idea is that wanteds should not be able to rewrite other wanteds. That's confusing. But maybe we need a whole bunch of these wanteds to rewrite each other in order to solve a type inference problem. If that's the case, then we end up with these derives. These derives can rewrite each other. In this case, we'll discover that they will that nothing good happens. The derives can rewrite each other. Here we discover that we can't solve the type inference problem, and instead we'll just report the wanteds. Turns out, though, that when we boil it down, the only reason that we have derives instead of just wanteds rewriting each other is to make for better error messages. And so it turns out that we can get better error messages another way just by keeping track of which wanteds have been rewritten by other wanteds. So this is it's one sentence, but it's a lot of work in GHC to do. And this is another simplification. Those of you who have written type checker plugins will appreciate this as well. So that's the two simplifications. I hope this has been an interesting introduction into how GHC constraint solving works. And I look forward to seeing you around the conference. Thanks very much.
Thank you very much, Richard. I'd like to ask you to head over to the sessions area where you can answer questions from our audience. We will take just a short break in broadcast and begin our next talk at 10 before the hour. Thank you.